Hello and welcome to Bay College's online lectures for intermediate algebra. Today we're going to look at section 8.4, which deals with logarithmic functions. The previous section was exponential, and now we're going to look at logarithmic functions. Well, what is a logarithm? Well, let's look at this example first. We've seen this in the previous section. We have an exponential function, and we found a series of points. Let's go ahead and do that right now. 2 to the negative third is 1/8. 2 to the negative second is 1/4. To the negative first is 1/2. To the 0 is 1. 2 to the first is 2. 2 to the second, 4. 2 to the third, 8. Now, if I were to graph these, we would get this graph right here. It passes through the point 0, 1. That's our intercept. Anything at 0 power is 1. So to find its inverse, well, if we recall from the section where we dealt with inverse in this chapter, we can find the inverse by merely switching the x and y values. So the first point, I just switched my x's and y's, and that's going to be a point of the inverse function. And I wrote it right here, x equals 2 to the y. Switch our x's and y's, that's what we're doing here. This would be 1/4, negative 2, 1/2, negative 1, 1, 0, 2, 1, 4, 2, 8. Now, if I were to graph this, I could plot all these points, but we already talked about inverse functions. And we know that inverse functions are a reflection through the line y equals x, our identity function. If I switch these, I still have x equals y, which is the same thing as y equals x. So we can do a reflection. And well, here's the interesting thing. We can graph something with only one point because we understand this concept. 1, 0, right? It's inverse. And now I can just draw the reflection. So it may not be to the perfect scale, but we can see what's above the line here is reflected below the line y equals x. So that's the graph of our inverse logarithm to this exponential function. Well, I'm using this term logarithm, but we haven't actually learned how to solve this. When we dealt with inverses, we always had to solve this for y when we flipped them. Well, how do we solve this? That's where we actually apply logarithms. So let's take a look over here at what a logarithm's all about. We dealt with this in the previous section, where an exponential function, the base is raised to a variable. Well, a logarithm, if we switch x's and y's, we have to introduce this logarithm, this new operation. So y equals log of the base b. Notice this had a base, b. This has the same base, inverse, but they still have same properties. The base is the same. And this x is my variable. Now, if we look at this here, x was the exponent, but when we switch x's and y's, this value is essentially an exponent. Logarithms tell us what the exponent is. Excuse me. And just to review, our base has to be greater than 0 and not equal to 1. Okay, because 1 to the whatever power is always going to be 1. So we've seen exponential equations. I'm just going to really quickly graph this. That's our exponential equation. This is the point 0, 1. What is its logarithmic function? Well, if I were to switch my x's and y's, I'd have x equals 3 to the y. This is where we introduce a logarithm. All I have to do is identify the base. Log base 3 of x is y. This is actually the new exponential value. This is my function. So, log base 3 of x. So how do I go about graphing that? Well, I realize it's its inverse, so I can essentially reflect it through that y equals x, and I have the point 1, 0. Same behavior. Okay? And we talked about domains and ranges of the exponential function. And we talked about increasing and decreasing. This here is an increasing logarithmic function. All right? And it has to do with the base. If the base is greater than 1, it's increasing. just like it was in our exponential functions. When the base was greater than 1, it was an increasing exponential function. But what happened when the base was between 0 and 1? Because we know it can't be negative. Well, when it's between 0 and 1, for an exponential function, it was decreasing. Okay, so this exponential function is a decreasing exponential function. So its inverse, a logarithm, the base in this case is 1/2 x. So I would read this as y equals log base 1/2 of x. How do I graph that? Well, if we look at this, we still have this point, and I'll write it over here, 1, 0, that's our part of our reflection. But now it's going to be decreasing. And hopefully we can see, yes, this is a mirror image through the line y equals x. What's up here is actually reflected down here as it goes positive in the y, it gets closer and closer to the axis. As it gets positive in the y, it gets closer and closer to that axis. So these are inverse. And here as it goes to the negative, it goes to infinity. And here as it goes to the negative in y, it goes to negative infinity. So they are reflections through that. Now let's think about these properties, all right? When we talked about exponential functions, its domain was all real numbers. Its range was from 0 to infinity. And we talked about y and x-intercepts for exponential functions. But when it comes to logarithmic functions, the domain, well, we only have positive values for x, because this is my logarithm right here. We only have positive values for x. So my domain is from 0 to infinity. And my range, well, my range, this goes all the way to positive infinity. It goes all the way down to negative infinity. My range is all real numbers. Now, when we do inverses, we don't just switch x's and y's, we also switch domains and ranges. And another thing is, if we look at our y-intercept, that also switches, doesn't it? From 0, 1 to 1, 0. That becomes our y-intercepts, becomes our x-intercepts. The y is 0 now, that's an x-intercept. What is my y-intercept for this logarithmic function? Well, it only approaches the y-axis, but never crosses it. And if you recall, when we dealt with exponential functions, their properties were the exact opposite. Domain and range were flipped. The x-intercept and y-intercept were flipped. There was no x-intercept in our basic exponential functions, like this here, never cross the x-intercept. So that's our properties. We've seen this before in the previous section when we talked about exponents. We can change our domains and ranges, change our intercept, and have a logarithm, inverse operations through that line y equals x. So what do we do with this information? Well, let's apply it to some equations here. If we know the opposite operation of an exponent is a logarithm, what we can do is we can rewrite exponential equations or equations containing exponents into logarithmic equations to solve them. Now this one here, hopefully we can see, yep, 10 squared is 100. We know this is a true statement, but let's write this as a logarithmic equation. In order to do that, just identify what is the base. The base is 10, so I'm going to write log base 10. We'll delve more into that log, it's a special one. Of 100 equals 2. Why did I write it this way? Well, if I know this is the base, it's also the base of my log, but logarithms equal the exponent. The exponent value comes over here. We're switching essentially our x's and y's. We're switching our values here, like exponent and the value. So we switch them. Log base 10 of 100 equals 2. Essentially, this says 10 to what power is 100? The answer would be 2. If we look at this, identify the base. I see the base is 8, so I'm going to write log base 8 of 164 has to equal the exponent, negative 2. Now here, maybe you can look at this and intuitively say, I know 3 to the third power is 27. But what if it was more complicated than this? Well, if we write this as a logarithm, identify the base of 3, so I'm going to write log base 3 of 27 equals x. I've isolated my variable. If this was a more complex equation, I could then solve this, whether I use a calculator or I use other properties of math, I can find out what this variable is because I isolated it. So we can see the usefulness, hopefully, of logarithms. Now let's look at this one. Very similar to the last one. I want to know what t is. I got to get it all by itself so I can use a logarithm. The base is e, so I'm going to write log base e of 82 equals that power of t. Switching my x's and y's, using that inverse. So, and this is something we could put into a calculator, and we'll discuss this because that, again, is a special log. Well, using this same property, sometimes we could even solve for a base maybe in some cases, in some equations. But for now, we're just going to see about switching this. My base is a, my power is 5, and it's equal to 4. So we're actually going the opposite way of what we just saw here. We took exponential equations and we wrote them into logarithms. And we can do the same thing if we have logarithms. We can write them as exponential equations. The base, the power, the value. All right, the next example here, well, my base is e, and my power is -3, and it's equal to the value b. Now this, because this was a logarithmic equation, and I can write it in its inverse form, e to the -3rd, that's something I can put into my calculator. I can figure out what b is all about. All right, we're going to do the same thing here, and this is going to show that these properties do hold true going back and forth from logarithms to exponents. Here my base is 5, and my power is 0. Well, what's anything to the 0 power? 1, right? So 5 to the 0 equals 1. That's a true statement. Let's look at this one here. My base is 8. My power is 1. 8 to the first power equals 8. Also a true statement. Now this one's nice and interesting. And in the next section, when we get into the properties of logarithms, this is going to make a little bit more sense because we can use something called the power rule. But anyways, let's stay on track here, not go on any tangents. If I rewrite this, it's kind of what I like to call the dust statement. It is what it is. The base is 4, the power is 3, and it's equal to this value, 4 to the 3rd. And that's why I say it is what it is. 4 to the 3rd is 4 to the 3rd. It doesn't get any truer than that, right? Well, let's look at this one for a moment. I identify the base as 2, and the power is 1/2, and that has to equal that square root of 2. Now, hopefully we remember when we worked with radicals earlier in the semester, we saw that radicals were nothing more than fractional exponents. Here, my index is 2, and my power is 1. 1 over 2. So this is a true statement. Now, I put this one here right next to this one so we can compare. If we look at this, the base is e, the power is -5, it's equal to e to the -5. If these bases are the same, let me just cover that up for a moment. -5 is -5. That's a true statement. We're going to talk a little bit more about that in some examples that I have over here on this end of the room. All right, so if we understand these properties of logarithms, and if you're not comfortable with them just yet, it'll come with practice, and here is some examples of the practice. A logarithm asks, 2 is my base, log base 2 of 16 is what? Essentially what it's asking, if we rewrote it as an exponential equation, is 2 to what power is 16? Well, we could go 2 times 2 is 4 times 2 is 8 times 2 is 16. I multiplied 4 factors of 2. Another way to do it, factor this down. How many 2's can you get out of it? 4. 2 times 2 times 2 times 2 is 16. So 2 to the 4th power is 16. So we can intuitively work some of these, find their exact values without having to go to a calculator or something like that. Now, if we look at this, hopefully we know our rules of exponents. Log base 3 of 1/3, what's it equal to? Well, what is 1/3? It is the reciprocal of 3. Well, the reciprocal tells me it's negative, and since it's 3 in both cases, whether it's 3 or the reciprocal of 3, the power is 1, so it's equal to -1. Is 3 to the negative first equal to 1/3? It sure is. Log base 5 of 25. 5 to what power is 25? Well, 5 squared is 25. So the logarithm base 5 of 25 must be equal to 2. 5 squared is 25. So we're checking. This one, hopefully we can see it. Because this asks, 2 to what power is 1 if we wrote it as an exponential equation? Well, any base to 0 is 1. So this has to equal 0 regardless of what that base is. Log of 1, regardless of the base, will always be 0. We'll look at that property right here in a moment. Here we have log base 5 of 5. Well, if we think about it, 5 to what power would give me 5? 5 to the first power. Now, if you recall before when I covered up my e's, my log base e, shortly ago, negative 5 was equal to negative 5. Well, in this case, the power here is 1. 1 equals 1, that true statement, right? Only if their bases are the same. So let's look at these three properties here. Log base b of 1. The log, regardless of the base of 1, equals 0, because anything to the 0 power is 1. So that's kind of a shortcut. If we recognize that property of logarithms, whenever I take the log of 1, it equals 0. Here we have log base b of b. Well, b to the first is itself. That's a property of exponents. It's also a property of logarithms. Anything to the first power is itself. And that applies here if we look at this. Log base b of b to the y equals y, because b to the y power is b to the y power. If we cover this up, since their bases are the same, y equals y. Think of this as reducing, right? Reducing to 1 when their bases are the same. Is that what happened here? You cover that up, it reduces to 1. Because that was the power. Here it reduces to the power, y equals y. That also holds true inversely if we have a base raised to the log of the base. Now this logarithm is actually in the exponent area. So I can just say, I can think of this as reducing. The answer to this is 16 when I simplify it. But let's prove it. Let's make sure. Because we have an idea of logarithms, let's just simplify this exponent. Order of operations would say you deal with exponents before anything else. So this is an exponent, let's deal with it. 4 to what power is 16? Well, I know that this is equal to 2. 4 squared is 16. So, what's 4 squared? Now that we've simplified this logarithm to 4 squared equals 16. Well, if I simplified this, a lot quicker method, 16 is 16, isn't it? All right, so let's use that property and apply it to this right here. I have 5 raised to the power of log base 5 of the quantity 4x minus 3. Well, I can't simplify this because I don't know what x is, but using this property, they have the same basis, it essentially can be thought of as reducing to 1. If I simplify that, the answer is 4x minus 3. Now, log base e. They have the same basis, so I can say, hey, the answer is x cubed. So a little shortcut, and that'll come with time. You'll be able to recognize those and just see them right away with practice. So this has been section 8.4, logarithmic functions. Thank you for watching.